If we were to make a graph of the force applied to a spring, causing the spring to stretch, and the distance that the spring stretches, we would see that we get a linear graph where the graph starts at the origin of 0, 0. That means 0 newtons of force stretching the spring 0 distance. It's important to once again stress that we're looking at the distance that the spring is stretched, not the actual length of the spring. This graph shows that we have a linear relationship then between the distance that a spring stretches and the force that the spring experiences. This shows a direct relationship. Now, we are not actually graphing the force that we pulled onto the spring with, but rather the force of the spring itself. We can do this by waiting for the mass to stretch the spring out to equilibrium, where the block will not be moving. If the block does not move, then there is no acceleration. So this block here is at rest, and it's going to remain at rest. This means the force of gravity and the force spring need to be equal, just as if this block was resting on the floor and not moving up or down in any way. This means my net force is 0. And the only way that is possible is if the force of the spring is equal in magnitude, yet opposite direction of the force of gravity. So the truth of the matter is, if I want to find the strength of a spring, I can't actually measure the strength of the spring directly. What I have to do is I have to apply a force to the spring that I know that I can control, such as the force of gravity of a block hanging from the spring, stretching it. And if the spring is in equilibrium with the object, if there is no acceleration, then by virtue of Newton's second law, I can then calculate with the force of the spring simply by saying that it's equal in magnitude and opposite direction of the force of gravity. It's important to stress that these are not an action-reaction pair. They're only equal in magnitude because the acceleration of the system is 0. Please notice, both forces act on the same object, which automatically means it cannot be an action-reaction pair, since they always interact between two different objects. Here we have a case of two different types of springs with very different stiffnesses or strengths. This right over here is a very weak spring that's easily compressed, easily stretched, and it's often used for the simple case of a ballpoint pen. If I was to graph the amount of force needed to stretch the spring, I wouldn't need a lot of force to stretch the spring a long distance. This type of spring is not very stiff at all. However, cars and trucks themselves have springs that attach the tires to the frame of the car to help absorb impact. These springs are incredibly strong, and they resist force incredibly well. These springs do not compress a lot when you apply a lot of force. These springs are incredibly stiff. We can calculate the stiffness of these springs simply by doing a ratio of the amount of force needed to compress or stretch the spring divided by the amount of distance that spring was stretched or compressed. So the slope of the line actually represents the stiffness. The smaller the slope, the less stiff you are. The greater the slope, the more stiff you are. Please notice, though, this stiffness is a constant for a spring. So often we'll call the stiffness a spring constant instead. We can always calculate the stiffness of a spring, or the spring constant, by calculating the slope of a force of spring graph versus the distance that the spring stretches or compresses. The equation for slope is, of course, the change in the y-axis over the change in the x-axis. And so if I look at this, I have going from 0, the force of a spring for my y-axis and the distance stretched for the x. So we can easily calculate the slope by saying it's the force of the spring divided by the distance the spring was stretched. This delta x here is from 0 to the point that you are stretched, not from 2 points individually. If so, I would have to find the change in the force, which we're really doing also, but the initial force is 0 if the spring is unstretched. Since I'm dividing force by the distance stretched, the unit for this would actually be a Newton divided by meter, the force divided by the length.